So this is, like I said, we're going to be predicting molecular color. Now, I call it molecular color because these molecules are not in a solvent. They're not in a crystal. So they're not in a solid or a liquid. This is a single molecule with no external fields. And so if you could concentrate that molecule without any external fields, you would get a color from the molecule. Now, it may be dramatically different if you put it in water or hexane or acetonitrile or ethanol, and there you're getting that solvatochromic effect. But if we don't even worry about the solvents, we just want to know the color of the molecule, then you can predict it with this. And then, if you wanted to look at the solvents, then you can maybe look at the solvation models in Excel and get a change in geometry, and then you could predict the color again from that. Okay. So here's the process. This is a little flow diagram. What I'm doing is really walking you through a poster that I made for the ACS meeting 2 or 3 years ago, describing this process. And people just love color, right? It's just around us everywhere, rainbows and blue skies and everything like that. And so this was a very weird and exciting poster session. I put this poster up and a few people came by, and then a few people came by and said, so-and-so told me to come see your poster, tell me about it. And then a few more people, and I don't know what you would call it in a poster session, but if it was an online thing, it went viral. I mean, I had a crowd around my poster because people want to know about how do we get color out of Gaussian. It was thrilling, So so I'm going to walk you through that poster, which really walks you through this process. So these are the steps. You're definitely okay with several of these. You know how to build a molecule in Gaussian now. You can optimize it. You can do a frequency calculation. Then you can do this UV-Vis transition calculation. ZINDO is the one we're using because it's so fast, and it has been very accurate in the past. But you could also do time-dependent DFT. So with the B3LYP, if you put TD in front of that, you can do a time-dependent DFT, and it will give you these visible transitions as well. I haven't done a comparison, a formal comparison of ZINDO and DFT. Also, configuration interaction with singles excitation, CIS, will give you the same kind of output. But for our purposes, ZINDO would be good enough. After the ZINDO calculation, you extract the lambda and the Fs. So these are the transition wavelengths and their intensities. Okay. So now we have our spectrum, our stick spectrum. We could plot those and we could get sticks for every one of the transitions. And you saw that in the last talk on nitroanilines. You saw those stick spectra, and then I had the convolved spectra and so on. And so then we convolve each of these with a log-normal line shape. Now for you guys, that's probably going to be the most difficult step, is typing that log-normal line shape into Excel. Because it is very ugly, and we'll see it in the notes here, but it's a very tedious calculation. You got to really work with your parentheses and make sure that you're taking the log of what you think you're taking the log of. Okay. And then we produce that visible absorption spectrum using our simulation techniques. So we've simulated spectra before. We can add that log normal line shape to every transition, and then we sum across all of those transitions and produce the visible absorption spectrum. Now here, produce higher concentrations. We know that absorption is linear with concentration, and so all we have to do is just multiply that absorption spectrum, those F numbers, those intensities, by constants, like double it, triple it, times 10, times 100, times 1,000. And so we can produce a range of concentrations. I do 10 concentrations, but I double it each time. So I go 2, 4, 8, 16, and so on. Yeah, so it goes up to like 1,024. And so I have, from one molecule, which you can't really see the color, to 1,024 molecules, now you can see a lot of the color. So we're just multiplying those absorption spectra by constants. That's what I mean by concentrating. Okay? And then we transform each of those into transmittance, because transmittance is what we need for the XYZ color scales. So you see now where we're going. We're starting to enter ASTM E308, converting these transmittance values into XYZ and then RGB. So after we transform all of those absorption spectrums to transmittance, then we calculate the XYZ values, the tristimulus values, using the that fitting those sum product formulas from the last lecture. Then once we have the XYZ values, we convert those to RGB using that 3x3 matrix from the International Color Consortium. Okay, so it's just a 3x3 matrix multiplication. And then we produce, just for I think, intellectual satisfaction, just to see the chromaticity diagram, we can compute those chromaticity coordinates, and we can plot that chromaticity diagram. You see that over here on the right. And then here we're at step 11. We can produce those RGB color panels for observation. So this can be as complicated as you want to make it. I wrote a macro to do this, and I can give you the macro that you can use to do that. But at first, we'll just do it by hand. And then sometimes we have a molecule that comes out colorless. The peaks are in the UV region. We see transition wavelengths, but they have an intensity of 0. Okay, so they have visible transitions with intensities of 0. And this is what we get a lot of times with azo dyes. So we know for an azo group, it's the end of pi star transition of the double bonded nitrogen that is the strong chromophore. But if you do this calculation for a planar azo dye, the F value, the intensity is 0. There's a transition there, say 500 nanometers, but it's got a 0 intensity because it's symmetry forbidden. It's a planar structure, and we don't have X, Y, or Z polarized light that can cause that jump. But an azo dye at room temperature is not planar. It's excited vibrationally. And so that's what I mean by the step 12. If needed, you can break the symmetry of the molecule. So we bump that azo dye a little bit. So we, instead of planar, we make it a little non-planar by rotating that dihedral angle, and then we recalculate the ZINDO. And then that peak, just the intensity goes straight up, and the end of pi star now is allowed because we've broken the symmetry selection rules, and everything's allowed. And then we recalculate basically repeat, all of the steps 4 down and break the symmetry. Now, this last thing, this produce partition function weighted spectra, we are not going to do that. Okay. We're probably not even going to need to break the symmetry. So we'll probably be done at 11, step 11. Okay. For our projects, step 11 is good enough. But one of these days, I'm going to hire a computer programmer to do step 13. Okay. Because what? So step 13, we'll talk about it in detail. We'll go through each of these steps, and when we get to that, you'll see why I need a computer programmer for that. It doesn't matter. Yeah. Python would be fine. Yeah. Python's the easiest to learn and the easiest to work on. Yeah. Okay. So let's do steps 1 through 3. This is very straightforward. You have your molecule, you build that. 6-31G, B3OIP optimization. You can do a frequency calculation. And then after that, the output of that, you can check for negative frequencies until you get a good global minimum here. And then you go into one of these 3 calculations. And this is the one we're going to use. We're going to use this ZINDO calculation. And these are the keywords that you'll pick in the little drop-down menus. On the ZINDO method, you'll see a little box that says, all transitions, singlets, triplets. We're just looking for singlet only because we're looking for absorption spectra. And so we have the singlet ground state molecule. We're going to singlet upper state. So we're just going to look at singlet to singlet transitions if you have an even number of electrons. If you're doing a free radical or something like that, then let me know, because then you might need to do doublet to doublet or something like that. But for all your normal organic molecules that are neutral and everything's spin paired, you got singlet to singlet transitions. And we don't want to just do the homo to lumo transition, right? Just the single one. We want to calculate a bunch. So I've put in here 20. So we're going to calculate 20 transitions. We really only need to model. To be safe, I go down to 200 nanometers. Even though visible region starts at 400, some of those peaks might tail into 400, and so I go down to 200. And below that, I don't even model those. So, but if we conclude 20 states, calculate 20 states, we're going to get those that go down into the hundreds of nanometers. And so you can just model the spectrum of all of the transitions down to 200 nanometers. So this is what we get, this output. We have this excited state, singlet A, here's the transition in EV, here's the transition in nanometers, and here's the oscillator strength. So these are the values right here that we will turn into our absorption spectrum. This is the wavelength and the intensity. So if we were to just plot wavelength and intensity, we'd have a stick spectrum, right? But we're going to convolve that with a log normal line shape. So this gets us through step 3. This is the computational piece. Any questions about this?
Why not try to do it?
Okay, let me just let me change OBS to show display capture. Okay, and I'm going to go to Gauss view here. Okay, so I'm going to calculate the ZINDO. So let's do this. It's on the method tab, and when you go to ZINDO here, this is the it's all grayed out. Why? So here's where you put the 20. You put 20 right there. You see? Solve for more states, n equals 20. And then it's not letting me. Actually, this is a doublet. This is an unpaired electron on this. This carbon only has 3 bonds there, so it's got an unpaired electron that's on there. So it may, yeah, I might just go with the default. But when I get the output here, if it's going from like doublet to quartet or whatever, that's a spin flip or spin change, and so I'm not going to model that. I'm only going to model the ones that are doublet to doublet. Okay, so you're only modeling because it's absorption. You can't have a spin flip and an absorption. So you're modeling doublet to doublet, singlet to singlet, triplet to triplet. Okay, not doublet to triplet or whatever, or singlet to triplet. There's like we talked about before, there's no phosphorescent analog to absorption. Phosphorescence is a spin flip and an emission, and there may be, but we would not be able to detect it, and it's going to be so weak that we wouldn't notice it. So it's just no spin changes with absorption. We'll just stick with that. So those are the selections that you would make. And so then here's the log normal equation written out for you. So you got all kinds of parentheses that you need in this. And go ahead and refer to a cell that's the asymmetry parameter so that you can calculate that. So then you would have that cell for each peak. So for each peak, let's say like peak 1, you would have lambda for that, F for that. Yeah, WP. Yeah, so then you have this delta lambda, which I think is given here as W. That's delta lambda, that's the width, okay, times that asymmetry parameter. And then this asymmetry parameter. So you have those 4 pieces. You have the wavelength of the transition, which comes from Gaussian. You have the oscillator strength. You have this delta lambda, and this rho. So every peak has those 4 things. Okay. Now, your rho 1 can equal rho 2, can equal rho 3. I mean, you can have one asymmetry parameter for the whole spectrum, which I would encourage you to do, and one uncertainty, one delta lambda for the whole spectrum. But each peak will have a different transition and a different intensity, obviously. And so this is the absorption spectrum that I calculate. Here's my transitions, these sticks here. I just went ahead and made them tall. I didn't actually compute the intensity. But you see this transition, as it's multiplied, gets stronger and stronger and stronger. And this, each one of these is multiplied by, 2, then 4, then 8, then 16, and so on, and it goes all the way up. And so you're just plotting the spectrum from 400 to 700, but you're including all of these other peaks all the way down to 200. Because these guys, contribute a little bit to the visible spectrum. It's overkill to go to 200, but that's just what I do.
Better too much than too little.
Yeah, that's right.
In that first equation, is that saying the exponent, all that?
Yes, all of that is e to that whole thing. So in Excel, you can use this exp open parentheses, so the exponential function in Excel.
When you say try to build that in pieces, like make sure the natural log of the lambda minus lambda I and the rho minus 1, which we're building in pieces, make sure that works, and then add outwards.
Yeah, so, okay, where's, like, in this whole thing, where's your x-axis? This is your x-axis right here. Right? That's going to be referring over to your wavelength axis. And all of these others are constants related to that particular peak. Make sense? Yeah. And that's why we can't have this asymmetry parameter equal 1. It can be 0.9, it can be 0.99, but if it equals 1, then this right here gives us an error. So we're taking the natural log of that, and so the log of 1 is 0, and 0 is in the denominator. So we're dividing by 0. So it can be 0.9, it can be 1.1, it can be greater than 1 or less than 1, it just can't equal 1. Okay. Okay. So that's our line shape. We produce the absorption spectrum. And then transmittance is equal to 10 to the minus a. And so we're just doing the log based. Actually, it could be e to the minus a because this is exponential. Well, no, we're just going to do it this way. That's the way I did it. It works well. Okay, so here's our spreadsheet. This is one way you could do it. Here we have, like I said, peak 1 has a center wavelength. The oscillator strength from the Gaussian calculations, the ZINDO gives you this. I put that in as my full width at half maximum, my W value, my width, and then this is my asymmetry parameter. And then this has that log normal, and here's your formula. Okay, that's my little eyeglasses. Put your eyeglasses on and look closely. It's right there in the notes, so you can check your work. Now, I did something funny here. I said, if is there error. I put a little error trap in there. You don't have to do that, but you got to understand what I'm doing with that. So this comma here is part of the if-then statement. Okay, and so this formula is a little longer than it needs to be because I have what's called an error trap. If I, if the asymmetry parameter or something like that is wrong, it doesn't break my spreadsheet. It just gives me zeros. Okay, so I'm saying if I put in a asymmetry parameter of 1, just give me 0 for everything, and it'll all go away. Okay, as opposed to divide by 0 error, and then I don't get anything, no plots, no anything. Okay, you don't have to do that, but it's a handy thing. Okay, so then converting to absorbance, it's 10 to the minus absorbance. And so I went ahead and put a -1 times absorbance. Okay, for some reason it wasn't happy with just the minus absorbance. Okay, and then we get into the colorimetry. So this is the stuff we talked about last time. And I have everything on one sheet. I've got my color matching functions down here, which again are 400 to 40, every 5 nanometers we have those color matching functions. I'm using this D65 illumination. I'll have to give those to you. So write myself a note. DW, give to students. So right here on this tristimulus value for X, I have that sum product of my transmittance spectrum for this original calculation times the X value here times the illumination value. So it's the sum product of all three of those arrays. And then I divide by the Y value times the illumination function. And that's the scaling factor in the denominator. And that gives me the X tristimulus value. Then for the Y, everything is the same, only it's the Y on top and bottom. And then Z, it's the Z on top and still the Y on the bottom. So these are those formulas, those tristimulus calculations. So, you know, these right here, the sum product formula is in that last lecture that we did. And it's a block, you know, in Excel, it's a block of numbers that goes there, and then comma, and then another block of numbers from the X values, comma, and then another block of numbers for that D65. So you have 3 blocks of references selected and put into that sum product formula. Okay. And then you close parentheses, and then you divide by the scaling factor. And then computing the chromaticity coordinates is very simple. Once I have these right here, once I have these values here, x, y, and z, then little x, little y, little z, so I'll just show right here, this chromaticity coordinates, this little x here is equal to, you know, big X over x plus y plus z. And so I can calculate the chromaticity coordinates. Now, notice I have, what is it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 11 rows here, the original plus 10. So I concentrated that absorption spectrum and converted every one of those absorption spectrum to a transmittance spectrum, and then calculated the color of every one of those concentrated spectra. So we're doing a whole bunch of conversions over to X, Y, and Z. I have the original X, Y, and Z here, and then for the, you know, this times 2, see here, so this is the original, then I have the absorption times 2, and then the absorption times 4, and so then that absorption times 2 is converted to transmittance, and that absorption times 4 is converted to transmittance. And so these get stronger and stronger in terms of their color. And you see it starts out as a pale yellow and goes down, and now it's starting to turn orange as you can concentrate it. Okay. And you can see on the chromaticity diagram, if I plot the little x on the x-axis, the little y on the y-axis, it starts out, it gets more and more dark yellow, and then it starts to turn orange. It starts out linear, and then it turns in this chromaticity diagram. Now, this is a violation of what many people will tell you. They will tell you that color is not dependent upon concentration, and that's only for dilute solutions. Okay, for dilute solutions, the color doesn't change. It just gets stronger. It's yellow, pale yellow, stronger yellow, and stronger yellow. But what happens with the transmittance spectra, notice here, this white curve is the original color, and then we double it, we go times 4, right? We go times 8. When we get to 8, notice this is starting to get close to 0, starting to get close to the baseline. At this point, we have saturation. For these right here, it's called saturation. And when you start to saturate those transitions, then the color starts to change. Okay. It doesn't change much because we're just taking out a little bit more blue, but once we start taking out a little bit of the green, then this spectrum starts to turn orange. You see, we're going along here, and then once this starts to curve, that's when we're starting to see saturation. And so we see a little shift in the color as we get to more and more concentrated. A lot of times people will incorrectly call that a solvent effect, but there's no solvent here. Okay, so this will help you determine whether a particular color is possible with a molecule even without a solvent. Okay. Okay, this is the spreadsheet that I built. You can build one similar if you want. You can make yours look however you want. If you want to lay it out a different way, that's fine. And when you do a little presentation on your molecule, it'd be great to see your version of this, okay? But there's a lot behind the scenes on this spreadsheet. This is the main page. This is where I type in my ZINDO output. So the ZINDO wavelength and oscillator strengths go here. I type in my full width at half max. I type in my asymmetry parameters. And then this is the front page, the main page. Then when I go to the convolution page, let me just pull it up. I'll pull up that spreadsheet. Let's see. Let's look at the azulene. So this is azulene, and let's make sure we can see that. Yeah, we should be able to see it. Let me shrink this down. Yeah, we're getting it. All right. Okay, so this is my main page. Again, all of the transitions from the highest occupied to HOMO to LUMO all the way to like 204. It's not going to change things, but and then I'm using a 50 nanometer width, an asymmetry parameter of 0.9, and this is the main page. So here's the convolution page. See, this is looking at main page A3. This is main page A4, main page A5. So I'm just pulling everything off the main page because I can paste my wavelengths and oscillator strengths onto the main page, and then I can create these various peaks. Does everybody understand this page? This is the convolution page. This is the spectral simulation page. And so if I were to create this spectrum here, I could come up here, insert this guy right there, and there's my spectrum. And if I wanted to put my individual peaks on there, I could go to the right and down, copy all of those, and click on here, and paste special, and say names in first row, new series, and then they're all on there, you just can't see them. All right.
So you rounded those numbers?
Where?
Your peaks. You're like...
These guys?
Yeah.
I didn't. I mean, just using the, I guess, no, it's general. So that's all I've got. Let's look on the main page. Yeah, they're 0.9 and 0.63, 0.39.
Well, if you go back to the convolution, right below it.
Oh, here?
Yeah.
Yeah, I did. Yeah, I don't exactly know why, but I did. Maybe just for display.
But
yeah.
like not necessary.
No, not necessary at all. This is your spreadsheet. None of this is necessary really except the procedural pieces. So convolve your spectrum with a log normal, and here's that log normal. I put the error trap in there. You do not have to do that if you don't want to worry about this error trap, okay? And so you can put that formula in, and then this is the absorption concentration. So this is I'm producing a single spectrum here, a single convoluted spectrum. So this is my spectrum right here. So I'm going to take that spectrum and multiply it by 2 and 4 and 6 and 8 and so on, however many ways I want to do it. So on this absorption spectrum, there's the original, and I have these multipliers up here. So I'm saying this multiplier, B1 times that convolution spectrum, and then this one is C1 times, and this is D1 times. And so I have all of those multipliers across the top, and I'm multiplying that absorption spectrum by a number, right? I'm concentrating it. If I have 1,000 times more molecules, I can multiply that spectrum of one molecule times 1,000. And that's allowed in absorption. It's not allowed in transmittance. Transmittance is a log-based concentration dependence. So I concentrate the absorption spectrum and then convert it to transmittance. So then I have a transmittance tab. So this is, I just have these concentrations up here just because I wanted to see them. But this is just 10 to the -1 times the absorption cell. And so this is the same block of spectra, but I'm just looking at that other sheet and changing the sign and raising 10 to that power. Okay. So that converts all 10 of those spectra, or 11 of those spectra, to transmittance. And then here's the colorimetry. I have those sum product formulas in here. And they have the illumination, they have the X value, they have the Y value for the scaling. You can see the color coding here, and it's pulling that transmittance spectrum. It's in black because it's on a different sheet. And so I'm just referring to the transmittance sheet, and I'm calculating the X value for that first transmittance spectrum. And then for the second one, and then for the third one. And just going along, and I've got all 10 of those colors, or 11 of those colors here. And then I convert them to the RGB values using this ICC transformation matrix. So that converts XYZ to RGB. So that's like step 9, I think, or so, 9 or 10. And then once I have the standard RGB values, I make them 8-bit because, they go from 0 to 1, and we want them to go from 0 to 255. And so then here's my 8-bit RGB values, and those are the ones that Excel understands. So I just have this colorimetry page that shows me my colors. And so then I just put all that on the main page here. So these are my concentrators here. I went ahead and created a little formula where I could let's go up by 4 instead of 2. So I changed that to 4, and now it really concentrates things. And then I'm going to update the colors with this macro, and it goes black because it's totally saturated and it's those peaks spread out, and there's no light that gets through. If you have enough of a substance, no light gets through. And so it's showing that it's going to the red, right? But it's so opaque that none of the light gets through. Yeah. If I don't concentrate it much at all, if I do like 1.1, so it just barely goes up, then it's white. I don't have enough molecules, and so you can play around with that too. If I put a power to 10 on there in case I really need to concentrate it, like my oscillator strength, it's a weakly absorbing thing, and so I could go up by 10, 1 times 10 to the first power. I could put a 10 here too. I think I could do. It'll go opaque pretty quick. Yeah. So those are all of the pieces in terms of modeling the color. Now this talk, we've got a little bit of time about this symmetry breaking business. Okay. So occasionally strongly colored molecules will be computed as faintly colored or even colorless. I found this by when I was studying this, I was trying to think, okay, what colored molecules can I do for the paper, right? So I want to write a paper on this. I want to pick some classic examples, and I did azobenzene. Just this molecule, you've got a benzene, an azo group, and a benzene. Okay, and this N to pi star transition is the strong homo to lumo transition, and it came out colorless. The F was equal to 0, and that can't be right. Okay, and then I got to thinking, how can it be colorless if it's one of the strongest chromophores that we know of, this azo chromophore? And I got to think, well, maybe it has to do with thermal population of vibrational levels. So think about that mass. These 2 benzene rings are oscillating around that pi bond. That's a dihedral angle. And at room temperature, well, you do the calculation, and that vibration is, less than 50 wave numbers, really low. And here we have at room temperature 207 wave numbers of energy. So this molecule is oscillating like that quite a bit. And the ground state vibrational wave function is still symmetric. So it's not going to break the symmetry. Remember, the ground state wave function looks like this. And so it's top row. But what's the first excited state wave function? Looks like this. It's not top row. And in fact, if you were to square this wave function, that's the probability distribution. And so that's telling me that I have molecules that are bent this way or bent this way, and no molecules that are in the middle. So I have, if I have this vibrational mode excited by one quantum only, 50 wave numbers, it's either this way or that way. It's not planar. The wave function goes through 0 at the planar structure. So that molecule in the first vibrational state is not planar. Isn't that weird? How does it get to the other side without going through the middle? That's where our thinking in terms of these quantum states is fuzzy, right? Because it's never planar. It's either on this side or that side. So it's behaving like a wave, okay? We think of this macroscopic molecule moving like billiard balls through the plane, okay? No, it's either on this side or that side. It's a wave. It's blinking sort of in its vibrational motion. Yeah, it kind of breaks my brain too. So don't go too far down that road. You'll hurt yourself. And so, but the point is, we have non-planar molecules at room temperature. How many do we have? Boltzmann's distribution. So that's where the computer programmer comes in. I know the vibrational frequencies. I know the spacings for all of these spots, all right? I know that delta E, okay? And I can calculate E to the minus delta E over KT. And I can calculate the partition function, or the distribution, the partition of the molecules in all of those energy levels. And I can tell myself how many are non-planar. And so I can scale that peak by the number of vibrationally excited molecules. Well, this is a big molecule, so it's not just this one, it's also the twist of the ring, or this kind of motion, the bending. And basically every vibrational mode under 200 wave numbers needs to be treated with Boltzmann's distribution. And I need to do ZINDO calculations on every one of them. So I've got to generate the vibrationally excited molecules in every one of their geometries and do another ZINDO calculation on every one of those. And then I need to scale them by the Boltzmann factor. So if it was a 10% chance of being in that vibrational motion, then I need to take the ZINDO spectrum, all those F values, and multiply by 0.1. Okay, and then convolve them with a lognormal, add them into the planar structure, and build this accurate visible spectrum of that molecule. But that would give you a really good color prediction, and that's, so this is sort of changing that vibrational mode. If this was benzene and I picked that vibrational mode, now it's a bad one because it's 900 wave numbers, okay? But the point is, down here at the bottom, it says manual displacement. You can set it to 1 and save that structure. So they've added this capability of changing the vibrational structure and then saving that structure, and then you could take that right into ZINDO, okay? But think of how tedious that would be. If you had 10 structures under 200 wave numbers, you'd have to do this 10 times, take 10 different ZINDO calculations, scale every one of them by the partition function, and then add in all those spectra, and then you would get an accurate color. But so that's sort of a picture of what we got. We got the planar structure, we have the vibrational deformation, and here's the symmetry broken input coordinates that go back into ZINDO. So that would be like a twist of that nitro group. But that's how we get this wonderful match. Like here's this is on that nitroaniline, and right here in this concentration range, it goes right through this great orange color. I mean, we see a great match of the molecular color for molecules like this. And just talking through this and sort of getting people to understand how the electron cloud interacts to produce color, but also the vibrational motions interact to produce color or change color. It's a pretty fascinating little piece of science. And so that's why that poster was so popular at the ACS, because they saw all the pieces that go into color, from the structure through the absorption spectrum through the transmission spectrum, through the ASTM, turning it into XYZ values, turning it into 8-bit RGB values, and then displaying it on the screen. And so I would like for y'all to build up. That's why we don't really have any more lectures set up. We're going to be doing Q&A and making sure your spreadsheets are being constructed correctly and well. And so I'm here to answer your questions. I think this is a great final project. And so when you're finished, you'll be proud of the mountain you've climbed. All right. So that's all I've got for this. And these are some applications. We did the color of that explosive, the TATB. And we did the color of the nitro loss of TATB and got this beautiful green. Pretty good match. This is not exactly perfect, but we scaled this a little bit and we got a nice color for these bird eggs. So this is biliverdin and protoporphyrin. And so for a molecule this big, you're going to need to use ZINDO instead of unless you're patient, you want to use the B3LYP. Yeah. So we did pretty good on these different colors. So, and then we did the body farm, human body decomposition, but we didn't show any of those pictures. So, but that was the title of the poster: bird eggs, bodies, and bombs. So, yeah, the color, molecular color. So it was a fun presentation. Dr. Gross told me that you're just punking me on that.
Is it possible on Gaussian, is it possible to have a charge on an atom?
Yes, there is. So if you have a charged species, go ahead and put it, like if it's a -1, like on the charge of multiplicity. So let's look at that here.
I think that might be what messed up my head.
Yeah. So under calculation here, right here, charge.
Oh my gosh.
Charge, and then look at the multiplicity. Used to, they would let you screw that up, but if I go to +1, it says, oh, now we've got a singlet. I've taken that spare electron off, and now everything can pair up, and I've got a singlet.
I think that might be.
Yeah, but like for oxygen, it's a triplet. So if you have what's called a diradical, that's a triplet. So we've got 2 unpaired electrons, even number of electrons, but a diradical has them unpaired across the molecule. So you may need to check into your molecule if it's one you're not familiar with.
It's just one oxygen has a positive charge on it, or I already remember the molecules, but I couldn't figure that out. But that's
Yeah.
That's so simple.
No, that's fine. Yeah, it was better to show you than tell you.